Let's take a look at another bug. This bug is about references, strong and weak. For this bug, we have implemented a simple game. And like all games these days, this game is based around microtransactions. The more money you pay, the more you can play, the more you can win. And unfortunately, like many games these days, this game really wants to encourage you to pay money too, in the form of those microtransactions. And so there's a couple of aspects of this game that really make it so that you should pay this money if you want to win. One of the aspects is the moment you disconnect from the game server, you're removed from the leaderboard completely. And the other aspect of the game is, as you continue playing, the factor that you have that identifies, or the factor that you have that's used to multiply how much your money actually, how many points you get for your money, decreases in time. In order to implement this, we implemented this with async IO. So there's quite a few pieces of mechanism here that don't really matter, like this mechanism here. Here's the tick. So every tick, you want to say, okay, take that factor and reduce it by an amount. And here is the connection mechanism for connecting. Well, on this line of code here, you added a callback. And you added a callback for that player to say, okay, take that player and reduce their factor every tick of time so that they have to keep spending money in order to keep up. And later on in this code, you tried to call the callbacks that you had registered there, but the callback was never called. With these two pieces of code, it should be enough for you to see what's going wrong. Can you spot the bug? Now, I'll give you a hint for this bug. This bug is all about weak references. When you have these frameworks that involve callbacks, one of the things that these frameworks are going to want to do is make sure that they don't keep things alive longer than they need to. They want to make sure that the callbacks that are registered don't prevent memory from being deallocated when that memory should be deallocated. So you can think as part of the game server, you have players constantly connecting and constantly disconnecting. Every time the player disconnects, you really want to clear out any memory you use for that player. Otherwise, your game server wouldn't be a long-running server. Every time a player joined, well, you'd lose a little bit more of a chunk of memory to store the information for that player. If you registered a callback every time a player joined, you'd want to remove those callbacks every time that player left. And so what the code does is it makes use of a weak set, a set that contains entries, but where the existence of the entry in the set doesn't force the entry to live any longer. And when the underlying piece of data is no longer needed, when that player is no longer needed, it gets garbage collected, and the weak set immediately reflects that by removing it from itself. So it's a set which elements can transparently drop out of as those elements are garbage collected. Well, here's a very small example of the bug itself. And in this example, what we'd expect is we add some object to this weak set, we remove the object out of scope. So we delete this object, and at this point in time, we see the weak set is empty. But the weak set is not empty. Here you see an opposite case of the bug that we had. The weak set actually has an extra element. Can you spot the bug here? And does this give you a hint for the original bug? Well, here's the answer for what we're dealing with. Whenever we create weak references, and whenever we write any sort of Python code that has to be just a little bit careful about memory, so not a short-running script, not some analysis in our Jupyter notebook where we're going to restart that Jupyter kernel every so often. Whenever we write something that's maybe long-running or that has some memory limitations because we have to work with very large data sets, we have to be a little bit careful about the lifetime of the data that we're working with. In the case of this particular program, we had a callback on a bound method of a class. So we have this player class, and we're going to retrieve from that player class the .tick method. We're going to add that to our callbacks, and we'll see it immediately get removed from those callbacks. We'll see it immediately vanish. And the reason that we see it immediately vanish is when you have bound methods in Python, the direction of what keeps what alive, what holds a strong reference to what, is a bound method. That is to say, an instance method just a regular def or async def method on any class, well, it'll keep the instance of the class alive. Of course it will. Because if, for example, you had the player object and that got deallocated, but you had an instance of, say, player.tick and you called that, well, it's going to be looking around for the information that was deallocated and it's going to get into trouble. So player.tick keeps a reference to the player object alive, but it doesn't work the other way around. An object does not keep references alive to instance methods. So in the original version of the code, you had something that looked like this. In this version, this would create a bound method for the tick method of this player object, and because nothing else kept this bound method alive, it would immediately be deallocated. And once it was immediately deallocated, it would immediately be removed from the callbacks weak set, and you'd see there were no callbacks, and no callbacks would be called. So the nature of the bug is actually the nature of the fix for this bug is actually quite simple. All you need to do is keep this thing alive in such a way that its lifetime matches exactly the lifetime of this player object. But as always, what's more interesting than the nature of the bug itself is the explanation and what that explanation tells us. This bug tells us quite a few very interesting and very subtle things. One, we cannot avoid thinking about lifetimes in Python. That is to say, oftentimes we write our Python code, and in our Python code, we don't really think that deeply about allocation or deallocation. It happens transparently in the background. But what we do need to think about is, what is the lifetime of our data? And so just to sketch out this example, we had some async def. And in this, we created an instance to some object. So we had some class here, and so we had created an instance of this object. What is the lifetime of this piece of data? Well, clearly, as long as the only thing that ever refers to this data are variables inside the scope of this asynchronous task, then the lifetime is the lifetime of this asynchronous task. So I can even show you where this thing gets deallocated. So here we'll see the deallocation. So here, and we'll run our asynchronous task. So you'll see this thing will get deallocated, and it'll get deallocated at the end of running this asynchronous task as everything is being cleaned up. So if I put one more print statement here, you should see that it gets deallocated before this print statement. But of course, if I put one inside the body of this function, you'll see that it gets deallocated after here, but before here. And so we can do just a little bit of printf style debugging to figure out when things are removed from scope. There's a couple other things we could do to maybe debug this to see if something actually got cleaned up. There's the GC module, and in the GC module, there's a get objects. And the get objects tells us all of the objects that exist alive in our Python program as of any one point in time. So we could do something like this. Grab get objects, and maybe iterate through this. It's every piece of data that's in my Python program that's alive right now. We could iterate through this, x for x in get objects. If it's an instance of our type, and you can see there's nothing alive here, but there should be one thing alive there. We can use the GC module to get the refers and to get the reference. And the refers and the reference are, I think I might be misspelling this, the refers and the reference. The refers and the reference are what's holding what alive and what is something being held alive by. So, for example, if we have some structure like, say, an object, let's create an instance of this object. Let's put this thing into a set. I'll probably have to make this frozen, so this will work. I can say, okay, get the refers for the object. And you can see there's quite a bit of noise here because one of the things, let's put this into a function because that'll reduce the noise a little bit. The global scope is that first very long entry. But here you can see the thing that's referring to object that's keeping it alive is this set. You can also say, what are the things that reference that the set is keeping alive. So you can do a little bit of debugging here to see what's kept alive by what. But whatever the case may be, when you're writing your code and you need to make sure that you don't have any memory pressure, because these things may be kept alive by circular references, which will eventually be garbage collected. So if you need to avoid running out of memory or memory pressure, well, you might need to use these different approaches. In the case of callbacks and callback frameworks, because callbacks and frameworks that use callbacks don't want to negatively impact the memory use of your program, they don't want to keep things alive longer, what they'll do is they'll use the weakref module, and they'll use things like this weak set. And so they'll create weak sets where if let's create a data class here. If I create a weak set and I put an instance of this class in that weak set, one of the surprising things that I might see is the weak set, and I've got to make this hashable, is empty. And the reason it's empty is, as of this line of code, nothing else is keeping this instance of the T class alive. Therefore, it's immediately garbage collected. Immediately garbage collected. But if I do this, well, this variable, obj, is keeping that alive, so it can coexist in the weak set. And that's really the nature of this bug itself. Well, this leads to some interesting consequences. And one of those interesting consequences are some transformations that we might anticipate are innocuous are actually not innocuous in Python. I'll show you one example from the code itself. And this may require that I run this code. So let's grab our code, and I'll show you one interesting thing. In an earlier version of this code, there was another bug. This line here that printed out the leaderboard was written like this. It would print out the top 3 players. So here, let's just get this going really quickly. Player score. We'll do the player.name. And let's make sure that I fixed the other bug. Very good. And let's just do something real quick. And we'll put this in verbose mode as well. So here we have an instance of our game server. Let's get an instance of our game client, Alice, using Alice's parents' credit card. Is like that. Alice disconnects. So Alice is now disconnected. And Alice should have been cleaned up from the leaderboard. That's how it's supposed to work. If I were to undo this transformation or just comment out these lines of code and restart my server, you'll see on disconnect, she should be cleaned up as well. Let's see, why doesn't she get cleaned up on disconnect? There might be another. That's good, that's good. She should be cleaned up on disconnect. That's a problem. So that must be, there might be another bug in here. Oh, maybe I need to, yeah, I just gotta rerun this. So let's get in there. And then on disconnect, she should be cleaned up. That she's not cleaned up suggests that there may be one more lingering bug in this code where something is holding open or something's holding onto that reference to that player. In the case of this transformation, the for loop will create a reference to this object. If that object came from let's see, where's that coming from? So we got to figure out where that's coming from. And what we'd have to do to debug this is we'd have to use the get reference. So we'd have to, in our tick, kind of print that out. But in the case of a transformation like this for loop, the variable assignment here is going to create a reference to some data. That extra reference might keep something alive longer than it's supposed to. So the actual correct transformation from, say, a list comprehension or a generated expression to a for loop should include the deleting of these references at the end of each one of the passes through this. Because otherwise, you don't actually leave the references in the state that you want. And so this is the correct transformation for this. In general, what you should think is this. When you're working with callback-based frameworks, which are very common, GUI frameworks are a notorious example of this, you need to track the lifetime of all the objects. You need to match up the lifetimes as close as possible. The reason that this trick worked is this created a local variable called tick, which kept a reference open to this bound method, and that variable only was in scope as of the duration of this entire asynchronous task, and that's exactly the same duration that the player object was around for. And so this matched up exactly to this. There are a couple of fixes that you'll see for these kind of problems, which say create a global variable or whatnot, which is not a good idea, because a global variable, the lifetime of that thing is going to exceed the lifetime of the underlying instance, and you'll actually end up potentially with memory leaks, or if you have like a global dictionary or global container of some sort, you'll end up with some kind of memory leaks. And you'll basically obviate what the weak set or the weak dictionary was trying to do in the first place. In the case of this for loop, even things like the variable assignment in the header of a for loop can keep things alive a little bit longer. And so when you run into these troubles, with long-running functions like asynchronous tasks that run in the background, that don't execute, run to completion, and then clean up after themselves, but are actually running consistently in the background, well, you have to be a little bit more careful. And the use of the GC module, for example, the use of GC get reference and get refers, can help you figure out what's keeping what open and to track this down. Now, in the case of this particular lingering bug with our client, I wonder if we can try and sort that out. So let's try and run our fix server and see if that's still present. So when Alice leaves, she should be cleaned up. Since she's not cleaned up, what we'll need to do is figure out why there is a reference held open, but we should be able to find that pretty easily right down here. So we should be able to do something like get refers for the player object at this point. And when we do that, we should be able to see when there's a disconnect. Oh, let's see, get refers. We need two R's unlike in HTTP. Okay, there we go. We should be able to see what is holding that reference open. And let's see what it is. So here we go. The bound method is keeping that open, so the bound method is still alive. So let's see if there's something keeping that bound method alive. And we'll disconnect. So here, that's the bound method. And is there nothing keeping the bound method alive? If there's nothing keeping the bound method alive, then we should see that everything should be cleaned up. And you just have to keep trying to trace this all the way back to the source. So we'll do that there. Okay. So you can see here this coroutine game.tick is keeping that alive. So why is that keeping that alive? Well, it's actually a smaller bug here. This for CB and callbacks, this callback object here is actually that tick, which keeps the player object alive, which keeps everything alive. And so, like I said before, you need to put a del here to actually clean this up. This may seem to be really tricky in practice, but in truth, really it is just a process of you find out what is keeping what alive using the GC module, and then you can track that down, see exactly where that is, and then clean that up. And you can see here, this is the final working version of this code where just one extra del. Or you slightly change the way that you write your code. This may be one more reason why you might want to do things like use comprehension syntax, because you can think that one of the advantages of comprehension syntax is variables that are, so self.callbacks, variables are contained to this scope. So this actually will be more nearly correct than this, despite it being a terrible habit to write code like this, because here you're clearly not actually trying to get the result of this computation, but this will should actually clean this up. You'll only get the result of whatever the callback is. So you'd have to do something like that. Don't actually do it like this, really just do the del. But you can see that there are some slight nuances when you're working with weak references, especially when you need to make sure that things get registered and unregistered and get cleaned up automatically. That's that takes us to the end of all of the bugs that we had for you today. Now, I know that there are more bugs that you've had to deal with, bugs in your code, as well as bugs that you might have spotted that we didn't catch as part of this session, or bugs that you ran into when you were going through this session. We've shared all of the notes for this material for you at the link below, as well as on Discord. And we'd love to hear from you bugs that you have run into in your code that you haven't quite been able to figure out, or bugs that you've run into that you're not quite sure, how would I go about figuring out this bug? We'd love to hear from you examples where those bugs might lead to some greater understanding, because part of this series is not just identifying the way that we do something right and learning from Cameron or myself writing a bunch of code in a blast and getting everything right the first time, but learning from when something goes wrong and trying to figure out what kind of coping strategies do we bring to that, what kind of concepts, what kind of thinking do we bring to learn from others as well as our own mistakes. With all of that said, I want to thank all of you for joining us for our session today. Do join us on Discord if you have any follow-up questions. We've shared with you all of the bugs and all of the notes. There's a lot going on in some of this code, and we'd really encourage you to revisit the code samples and to think a little bit about why is it that the code might have been written in the way that it was written? Was that in order to avoid possible bugs that could come up, or maybe that was written just to lead you down the false path of thinking something's a bug when it really isn't? But whatever the case is, thank you all for joining us, and I'll see you all next time.